Then you figure out which one is working and which is not working. That's what I would do. So I would again start out with the phase. Typically, the problem happens, okay, if there is noise and if there is a sharp gradient. These are the two cases when these unwrapping programs fail. So you could actually set up, test phase profile, uh, maybe pretty high, maybe 10 pi, 20 pi, 30 pi, and with sharper and sharper gradients, and also add noise to it. So you know everything about it, and then you wrap the phase, which can be easily done, and then you ask the computer to unwrap it using, either Puma or the Goldstein or whatever, and compare the results.
If you continue, I'll join.
Okay, okay, all right. So maybe we can get started.
Yeah,
I think are the
start.
online people
Yes.
there?
Yes, they are there.
Oh, they're there. Okay. All right. Yeah, that's what I was thinking. I didn't know. Okay, sure. Then I'll see you in like an hour or so. So this part over here, so Professor Nischal was also talking about applications, and I'll talk about a particular application, in this case of holographic interferometry. Okay, so this is a real life practical application in a project that we had, and this project had to do with finding the deformation, really finding the deformation of an airplane in a wind tunnel. Okay, so that's the application. So first, as you know, so let me go back to here. So first, you know that holography certainly is useful in reconstructing the 3D shape of the object. Everyone knows that. This holographic interferometry, as Dr. Nischal also pointed out, is useful to determine the change in the shape, okay, to a good deal of accuracy. And accuracy is of the order, of course, of a wavelength or so, right? Very small changes. Okay, so the basic concept, is to compare the holograms of the object. I mean, this is one way to compare the holograms of the object formed at two different states. Okay, now this comparison of holograms of objects at two different states typically is done, as Dr. Nischal said, and that's what I'm going to show, by generating an overall interference pattern when you read out the holograms. That's one way to do it. Another way, if you just want to figure out similarities between objects, okay, similarities between 3D objects. One of the ways we have, developed is correlation of holograms. Now, correlation of pictures, right? I mean, the amount of correlation, if it's higher, that means there is more similarity, right, between the two pictures. But 3D objects are not pictures, right? So what you can do instead is reduce the dimension, in a sense. That's how I look at it. So how do you reduce the dimension? By making a hologram, okay, of the 3D object. When you make the hologram 3D object, you have a picture. And then you can compare the two pictures. And if you see the correlation between the pictures is good, that means there is more similarity, right? And I'll show you some examples of that later on as well, because that's a useful tool in like facial recognition, all right? Okay, but before that, okay, so in holographic interferometry, as you know, you compute the phases of numerically reconstructed holograms and calculate their difference to yield a 3D map of the change, and that's commonly done in digital holographic interferometry. You can do it using analog principles. That's really what was being talked about yesterday. And this example I'm going to show you is analog holographic interferometry. So in here, what you would do is, first of all, either double exposure analog holographic interferometry. So here, you have two holograms for states 1 and 2 stored using double exposure, and then you reconstruct it using a reading beam. And then the two holograms produce, as you know, two different sets of diffracted optical fields. And those two different sets of optical fields are going to interfere. Okay? And they will form an interference pattern which will be superposed on the reconstructed image. And then you can record that digitally, you can record that, you can then analyze the fringes on it and figure out what's the kind of deformation. Another way you can do is this real-time analog holographic interferometry. So here you are not storing the two holograms, but what you're doing is you store the hologram for one state, which is formed by the reference and light that's scattered from the object in state one, and then you read it out by optical fields that have both the reference, the same reference as before, and light from the object at state two. So you make a hologram with reference and object at state one. You store that one. Then you read it out simultaneously with the same reference and from the displaced object. Okay, got it? And I'll show you that one because that's what we use in this particular example. So then the pertinent interference pattern can be digitally recorded in real time as it is happening, like a movie. And then you can analyze the fringes and say what's happening, how the object is evolving as a function of time. Does that make sense? So this is actually the technique that we used in our work. Okay. So here is actually a setup of a real-time analog holographic interferometry. So what did we do here? So first of all, so here is a laser, okay, and then there is, of course, the reference beam. Reference beam is going this way. Part of the beam is broken up by a beam splitter, falls on the object for which we want to measure the deformation, and the reflected light from the object, these two over here, they make a hologram that's stored in what we called a holographic camera. Now, what's a holographic camera? Well, you can use, a photorefractive device. That is a holographic camera because it stores, the grating. Or you can use some kind of photothermoplastic. Those are also around. They're kind of thick, materials. Both were used in this particular case, just to compare which one is working better. And then this photothermoplastic, of course, that's a special material. This was actually provided by a person from Moldova, one of the Eastern American, you know, uh, Soviet Union republics. So, or Eastern European, I should say, republics. So they are kind of specialists in making these kind of stuff. But both of them were used. So now here is the principle. So once you have recorded the hologram from the state one of the object, okay? So then what happens? Okay, if you keep the same reference, right? If you keep the same reference, and always assume that the reference is of course much stronger in intensity than that of the object, right? So then this same reference, when it reads that grating, what's it going to do? It's going to scatter the light into the diffracted order, right? So then that readout, okay, that readout would be a replica of the original state of the object. Now, on top of that, let's assume that this object is just moving a little bit, moving, changing, distorting. Then the light from here, okay, yes, it's also going to try to read the hologram. Now, this light is, of course, yeah, this is reflected. Well, good question. I'm coming to that. If you consider it to be entirely reflected, the calculations are different from when it is diffused. So in this particular case, we assumed a diffused object. I'll show you in the next slide. So we tried to do it with a reflective object, did not work. So then we tried with the diffuse object. Okay, so this light over here that is from really, you can call it scattered now. Scattered, really reflected, but scattered from the diffused object, okay? When it's displaced, when it is displaced, it goes the same direction. Now, of course, what happens is most of it will go in the same direction as the original light that had been scattered from the reference via the hologram in that direction. But then there is, of course, a small amount of light that will also be diffracted in this other direction. But the amplitude of that is much weaker because this light's intensity is much weaker than the other light, right? But if you just look at this direction, okay, which is the direction written as S, okay, then what you have here, these wave vectors are essentially kind of representing the wave vector for the scattered light from the state 1 object and the scattered light from the state 2 of the object that's going directly through. And then, of course, there is going to be a difference in the wave vectors. And that difference in the wave vectors will appear as fringes. Okay, does that make sense? So that's what is really done here. The other thing you can also actually do here, this is kind of on the side, is, when we do this experiment, of course, this is called a hollow camera, yes, understood, but hollow camera has a finite thickness. Like if you use this photothermoplastic, well, it's about 2 millimeters, 3 millimeters thick. Anytime you write a grating and you read out the grating, you also see higher orders because the grating, there's a Q of the grating, the Klein-Cook parameter. Klein-Cook parameter is not that high, so you see higher orders. And as it turns out, if you do this experiment, you are going to see light coming out this way from this reference, light coming out that way, which is the reconstruction of the object. And on that, you'll see the fringes. But also, you're also going to see light going in another direction here, another direction there, and so on and so forth. And as it turns out, the light going in this direction is like a phase conjugate of the object. Light going this side is actually called the phase enhancement of the object because the phases are added up. So these are some things to realize over here. And this is the experimental setup. So this was set up in our lab. But let me actually point out. So these are actual real life experiments, right? We are doing. So of course we have a Heaney laser that was writing the hologram. This particular setup, we had used the hollow camera comprising the photothermoplastic. We have also done it in green, where we have used the photorefractive crystal, like lithium niobate crystal. But here is something interesting. Okay. Um, this is an airplane. You see this blue guy here? This is an airplane. All right. So we are testing it out in the lab before the project finally was delivered to the facility. It's a NASA facility that has wind tunnels, all right, because that's where this is supposed to be. So wind will be going over, these model aircraft at high speed, and there are some windows on the side from which you have to shine the laser beam and diagnose, how the aircraft is being disturbed. So this is a real life application. So this model aircraft, as you see in blue, right? This was a toy aircraft bought from Walmart. Okay, so when we went to Walmart and we bought this, that's the best we saw. Didn't the initial experiment didn't work too well. Why? Because this was a very reflective surface. Right. It had a very shiny blue color, as you can see. And the reason is because really, this was really acting like a mirror. And so if it acts like a mirror, you just see the, kind of tilting of the mirror. You don't see the deformation, kind of interference patterns in detail throughout the body of that aircraft. That's the main problem. So it's just as if you put a mirror there. Okay, so then what did we do in order to make it a diffuse object? We bought spray paint, okay, and sprayed on it. So if you put spray paint, you see the particles of the paint are, coarse, and you're spraying it. So then it becomes a diffuse object. Okay, it's cheap ingenuity in a sense. That's what we did. So now the blue airplane became this silver color airplane plane after spraying, and then it worked perfectly. Okay, so now the experiment had to do with finding out When an aircraft travels, as you know, there are three quantities that people are interested in. They are called the pitch, the yaw, and the roll. Okay, so when this aircraft, okay, if you look at it, the vertical axis, in this case, the y-axis, then, the rotations, okay, the rotations correspond to roll, pitch, and yaw, depending on about which axis the rotation is taking place. All right, so those are three independent variables in angles. Are you okay with this? So this experiment was set up in the lab. So now you have to hold the airplane, right? So you put what is called a sting. Sting means like a rod. You hold a rod and then attach it to the airplane, and so that it's pointed in this direction exactly. And then the experiment was done. And so, for different configurations, okay, of rotation of the airplane's axis, you saw or we see all these different lines that are superposed on the body of the airplane. Okay, so this is a real life pictures. And you can do it in real time. How did we do it in real time? Well, all we did was we put a big fan, okay, like typically you would do in a wind tunnel, and then the aircraft would be, moving in all directions. And so these patterns would be changing. So we would be recording them, and after recording them, they will record as a movie. Then at any point in time, you can analyze the pitch, yaw, and roll. Are you okay with this? So as you see, this has very practical application. So one of the things I would like to point out over here, see, if you have, in this particular case, if you have, and this is a lot of analysis went on. If you have pitch and roll, so what is pitch and roll mean? So this one is pitch. That means if this airplane rotates about the x-axis, so if it's like this, pitch means, nose up and nose down. Okay, that's what is pitch. And roll means like this. Okay, so if you have pitch and roll, you see fringes like this, okay, which are linear fringes. Okay, you see linear fringes throughout the entire body of the aircraft, like so. On the other hand, if you have pitch, roll, and yaw, okay, pitch, roll, and yaw, okay, that means all three angles are changing, then you see these kinds of patterns. Again, straight lines, okay, but straight lines with one angle in this direction, one set of angles in the other direction, okay? And then if the entire airplane is deformed, how does it deform? When an airplane takes off, you look at the wings of the 787, change in height by about 6 feet. So that is the deformation. So when that happens, the curvature manifests itself in these curved fringes. So these are the initial observations. So now the question is, how do you analyze from here the pitch, yaw, roll, deformation, and so on? It's a very practical mechanical engineering problem, but it has to be done. Okay, so the fringe analysis for the airplane goes as follows. So here, I'm going to show you a very simple calculation that was done. And you don't want to get to most complicated calculations. No, I mean, this is going to be applied in industry. Okay, I mean, you don't go with a program that runs forever. So here, this is the way to analyze it. And this is something we developed by ourselves. Okay, I mean, again, no reading anything. It's us. So, if you have diffuse reflection, then you can think of the diffuse reflection from the rough surface as, radiators from different point sources on the object, right? Different point sources on the object. So consider one point, like this point P, which has a certain coordinate, like x0, y0, and z0. And let's assume that this point P has moved to another point, okay, call that x0 prime, y0 prime, z0 prime. Then, if you have a reference wave going at a certain angle, you can find out the interference pattern, right? You can find out the interference pattern between this reference wave and this point source, right? So what is that going to give you? That's going to give you a set of, like Fresnel zone planes, that kind of thing. And the final hologram, if you wish to call it, is a combination of all of these zone plates from every point on the object. Now, on top of that, assume that this hologram is made, then as I said, it is being read out by this reference beam and then interfered with light directly from this other point source, which is assumed to be the displacement from P to P prime. Then you can add up the two waves that are going to interfere, which I had drawn in the previous diagram in this direction, right? So one is the readout from the hologram. The other one is the complex field from the displaced points. So that interference pattern should be the fringe pattern, right? So that fringe pattern can be expressed like this. Okay, like this. So what are the terms over here? Well, first of all, it's x, because it's a function of x, y, and z also. So, so it's x, and then here you also have the x0 and y0, which are the initial positions of that particular point. Then you have the change of the position, like delta x and delta y. And this part over here is the distance. The z or z observation is the distance from the origin to the observation plane, and z0 is the distance from the origin to the z position of that point. So this is the part that is going to give you the linear fringes. And you see there is this other part over here, which gives you the circular fringes. These circular fringes really come from the deformation, as it turns out. And this part over here comes from the change of attitude of the airplane. Okay, that's what it is called. Okay, so one of the things you can do is you can probably find the slope of these fringes. And from the slope of the fringes now, you need to solve for the roll and pitch and the yaw. Okay, that's what you need to do. Because all the information you have is the slope. Slope and the period. Okay, these are the two information that you have. So you have the slope and you have the period along x, period along y. Okay, fine. But here is actually a practical problem. So, you know these guys. Okay, you know like delta x, delta y, delta z. Okay, and you need to solve for this delta phi, delta theta, and delta psi, which are the pitch, yaw, and the roll. Are you okay with this? So you see, this is a matrix vector equation, like a matrix equation, but this equation is unsolvable. So that's the problem. Why is it unsolvable? Because you see the determinant of this matrix is 0. Yeah. So you need to put in some other parameters. What's the other parameter you have to put in? And this is something we have to teach ourselves, which is a rigid body assumption. That means, the total changes at a certain point multiplied by their coordinates is equal to 0. So that's a rigid body problem. That is the airplane. Yeah, it's maybe flexing a little bit, but it's not like really bending out of shape. So under those conditions, you can actually solve for it. And then after you solve, the rest of it, is some results, which I'm going to show you here. So you see for here, these particular things. So this is the case, okay, this is the case you see where we took, go back a couple of slides where I told you what they were from. These kinds of things come from pitch, roll, and yaw. So in this particular case, we were looking at an example where you have those kinds of fringes with one slope on one side of the wing, another slope on the other side of the wing. So we have to take two of these points, and around those 2 points, we have to do some amount of analysis. Okay. In this particular case, we assume no roll to start with, but later on we flexed it to having pitch, yaw, and roll. But then, the fringe analysis really means that what you need to do is at a certain point over there, you need to find out the period along x and the period along y. Okay, and you also need to find out the angle. So you need to write some software program. So the way to do that is we took this one and put it through a rotation matrix such that the fringes, say, became vertical. Then we know the amount of rotation. Then once it was rotated, you can find out the period over here. And once you know the period here, you can work back and find out the period along X and period along Y because you know the angle of rotation. Does that make sense? So all of this had to be improvised in the lab. Okay, no one was there to tell us anything about it. So then, here, as you can see, these are standard, kind of results. You find the fringe angle for one case, you find the fringe angle for the other case. As you can see, in this case, the fringe angle was like 135 degrees because they're, in this direction. Here, the fringe angle is about 45 degrees. From there, you also can work your way all the way through, and then you can find out the amount of, the pitch and the amount of yaw. All right, and this is all based on that very simple matrix analysis. It works very well. So are you okay with this kind of analysis? So it's one thing to do the it, as Dr. Nischal was saying yesterday, to convert it to actual real life data is not the easiest. So that's something you need to, as you see, depending upon the situation, you need to work it out, right? And this is a very practical, problem, right? Now, we also did the case for pitch, yaw, and roll. Okay, the pitch, yaw, and roll. So this is also an interesting thing. You see here, I wrote something like a great circle. So what does that mean? That means if I have a point here, okay, if I have a point here is displaced, okay, then the shortest way to go from this point to that point as a result of the distortion is on the great circle because everything is going on a sphere. So if you take that assumption, then you can also find out how much would be the change in pitch, yaw, and roll. And of course, you get different answers. Now the question would be, you go back and ask your, um, people at the wind tunnel, which is happening, which is more close to the actual situation. If it is like this, okay, then you have the answer. If it is like something like this, they tell you, okay, there is no roll, then there is only pitch and yaw, then there is this set of answers. Are you okay with this? So the point I'm also trying to make here, okay, the point I'm trying to make here is, so this area of holography and optics does not stop only in the optics. You have to know a lot of the other things, where you're applying it to, right? I mean, as Dr. Nischal was saying, these are used to measure, some flow somewhere or, some contamination somewhere, or, these kinds of things are also very much used to measure the accuracy of auto parts, okay, in auto companies. Germany is one place where they use it a lot. So you have to apply it to that situation. Are you okay with this? So this is, by the way, another experiment. For those of you who are in the academia, this is another experiment you can set up in the lab and you can do it. Because you see, we did it in the lab. All you need to do is buy a toy airplane, set it up, put a fan, and fan is good too. It blows air, it'll be cooler. And then, you record the hologram and then reconstruct the hologram.
As we generally see the 3D perception, so what our brain actually, there are same certain types of phase unwrapping algorithm that run by our brain.
Our brain typically actually does this stereoscopic vision. So it sees, one depth through one eye, another depth through another eye, and then tries to judge the depth.
Still, those who use their only one eye, another eye is not in one. They have also the 3D perception.
Little bit, less.
Less,
Yeah.
they have
And their 3D perception, I've never talked to them, but their 3D perception may come from the fact that, one part of the object is more focused than the other. Because if you have a lens, I mean, so, it's a one object distance will give one image distance. The other part will not give the same image distance. It will be blurred.
Also, relative movement while they are in motion. That would change the
That would change, yeah, correct. Right. So are you okay with this example here? Any questions on this example? But as you see, it's a very practical example. You can apply it. Yeah.
Each node chain,
I'm sorry.
each is node chain, whole and yaw.
So there, I always confuse between those words, so I'll have to, and I'm not in aeronautical engineering. So here, so you see, the roll is, so if your airplane is like this, roll is like this, pitch is like so, and this other one is going like so, the yaw. See, the yaw is, see the rotation around this, so this is the z-axis, this is the z-axis, the rotation around the z-axis. Okay, so if this is the airplane pointing up, right? So roll is like this. Roll is like this, left bank, right bank. Pitch is nose up, nose down. And the yaw is the entire airplane swaying like this. The airplane was heading, say, north, it moves to northwest and northeast. So that is the yaw.
So how do you disclose that data?
This one, oh, in the real wind tunnel, they have a very similar setup. So they have the model airplane and they have this, what they call actually, the technical term is sting. It's a big rod. So the rod is attached to the end, one end of the wind tunnel, from where the fan actually, the same place where the fan starts blowing the air. So then the airplane is like this, and then there is a long rod, and the wind is coming from that side. So that's how it's set up.
In that case, there would be setup also.
I'm sorry?
There would be movement in that setup also.
Yeah, there is.
That we are considering here.
We are not considering here. I mean, the whole thing can move all the way starting from here. Yeah. So you can do that. You can compensate for that. Sure. That can happen. But I mean, you have to start somewhere. But before that, they did not have too much of these interferometric techniques to measure the pitch, yaw, and roll. So typically, the wind tunnel is a closed wind tunnel. So for this, what they have to do, they have to cut actually windows on the side because the laser light has to go and fall. So there are small windows that were cut.
Professor, could we not isolate each of these movements?
Well, I would say yes, but then they have to do that. I mean, they have to do some kind of a restrictive setup to do that.
But if you said that there was a rod which you can change the orientation in whichever axis I want. So I guess then isolation should be a possible.
So you could actually constrict it by holding the wings, in one place, then right, and then it will only go up and down. But that actually introduces more complications because you're putting more obstructions in the wind tunnel. Right. So that's the problem.
And when we are using an actual air tunnel, we would see interference patterns in wind itself.
Well, that depends on the wavelength and the frequency of the light and so on, how much the light is traveling. So here the wind tunnel, this particular wind tunnel was about this wide. Okay, and yes, I mean, that would happen, of course. So there is the turbulence from the air, but in that small distance, okay, I mean, we saw that there was not that much. But those are other things to consider. I mean, so this was for, okay, I mean, this is drawn as a fighter, but this was like a more subsonic aircraft. But, this was supposed to be developed for much higher speeds. In that case, yes, that would be a much bigger problem. You have to take that into account. So these practical situations are actually, as you said, too, quite different from lab experiments. But lab experiment is a start. But, I mean, anytime you develop any kind of new airplanes or anything like that, it has to, go through these steps. And there are plenty, I'm sure, of wind tunnels here in this country. So, these are good applications. Right. Okay, let's move to the next topic. The next topic I wanted to talk about was the phase shifting digital holography or phase shifting interferometry. It started from there. So the concept is again very simple. So here you see, in phase shifting interferometry, your objective is again to find out the phase. Okay, that's the bottom line, finding the phase. So typical interference patterns result, as you know, from the interference between reference and object wave, the same old thing, right? And of course, it is the magnitude of r plus o squared, the same old equation, which you can write in this form, which you've seen before, right? And then, of course, there are the four terms, as you see here. And these last two terms can be either written like this, or it can be combined to be written something like so, right? This cosine of phi o minus phi r really comes from the relative phase subtraction between the phase of the object and the phase of the reference. And of course, what you want to do is you want to find the unknown phase, the phi o, right? That's what you want to find. Because once you know the phi o, and from knowing, this guy, and you know this guy because, you can measure it. This is the intensity of the light from the object. You can measure it. So if you are doing a holographic experiment, okay, you just shut off the reference. You shut off the reference, then you measure the light that is only falling from the object. So that is the object intensity. So if you know the object intensity, you take the square root of that, then you get the magnitude of the object field. And if you can find the phi o, which is the phase, then the complex, object field would be the magnitude of EO times e to the j phi o, right? So that's my complex field. So that's why, people want to know what the phi o is. So here is something interesting. See, look at this equation here. This was something that was done for the first time by this Japanese guy. So his name is Yamaguchi. Okay, and this is a classic paper that appeared in Optics Letters in 1997. And it's very simple, actually, really simple. So what he said is, so we need to find this, right? We need to find what phi o is. So let's look at this expression, look at that expression, and let me set, just for fun, let me set phi r to be equal to 0. Okay, let me set phi r to be 0. Now everything is relative. Okay, fine, understood. I mean, phi r may not be 0. Okay, maybe something else. But okay, let's just take a simple case. Phi r equal to 0. Okay, phi r is equal to 0. Let's see what the value of the intensity is. Okay, the value of intensity I write as I1. So what would happen here if phi r is 0? This just becomes the cosine of phi o. Right? As simple as that. So that's my first line. All right, fine. So now next, look at the next one. Let me change, if possible, the phi r to pi over 2. Okay, so what I'm doing is between the first and the second, okay, I'm changing the phase of the reference by 90 degrees. There is no need for phi r to be starting with 0. It could start from anything. But the next time I change it by 90 degrees. I just took it to be 0 for simplicity of calculation in the first place. So if you put 90 degrees, so what's going to happen here? Then it's going to become cosine of phi o minus 90. Well, cosine of phi o minus 90 is like a sine, right? Because the cosine has been phase shifted by 90 degrees. So what do I get for that case? I get another value of the intensity. If you work this out, it becomes very similar to this. The first two terms are always similar, but the next one becomes plus 2 ER EO times now sine of phi o, right? Okay. Next time I change it to pi. If I change it to pi, of course, if you add and subtract pi from an angle, the cosine will still remain a cosine, except its, polarity will change from plus to minus. So now this time I have the same sum over here, but now instead of plus, I have minus, and then cosine of phi o. And the last, I take it to be 3 pi over 2 or minus pi over 2, whichever, the same thing. So again, it'll become a sine, and in that case, the sign will have an opposite sign, like minus, right? So I have these four, okay? Four are not necessary, but okay. Three are enough, but four, okay, is easier. Okay, if you do that. So now see here, if I subtract I2 and I4, so I2 minus I4, if I subtract these two, okay, what happens? The first two terms, of course, cancel out. What am I left with here? I'm left with 4 ER EO sine phi o. Okay, are you okay with this? Same thing, I subtract I1 or I3 from I1. What do I get? Same thing, but now times cosine phi. Well, divide one by the other. Guess what? You get the tangent of phi u. And the tangent of phi u is very simple. I2 minus I4 divided by I1 minus I3. So what does that say? That, well, isn't that a neat way to find the phase? I mean, so I have automatically found the phase from 4 measurements by doing, as you can see, 3 successive phase shifts of the reference beam by 90 degrees at a time.
Reference given object wave are taken from same laser.
Yeah.
Maybe it fits like phi r and measuring phi 0, like 40, phi 2.
Oh, this one, because the phi r could be really any number, but only thing I'm saying is this was for simplicity. I took phi 0 to be 0. But phi 0 may not be 0. I mean, it could be any number.
But
But
interested to find phase related with object.
right. I want to find the phi o. I want to find phi o. This phi r really can be anything to start with, but the only thing I need to do is change phi r by amounts of pi over 2 3 times. Okay? That's all I need to do. And if you take phi r to be 0, okay, as I did here, the final phase I am finding this phi o is of course relative to the initial phi r, which I have taken to be 0. But that's more than enough. I just want the relative phase.
0 pi by 0 not twice.
Right, right. All it changes is the pedestal for the phase, but I don't care. I mean, I need to know the spatial variation of the phase. But the thing here, that's another important thing which people do not talk about. So have I found the phase of the object? No. I have found the phase of the diffracted field from the object, right? Because that's the place I'm interfering it with the reference wave. So if you look at this diagram over here, right? If you look at this diagram, so okay, here is the argon laser, whatever, it's broken up, say into 2 parts and so on. One part is like this reference guy, okay? The other part is going to the object, and this is the light that's being reflected from or scattered from the object, going all the way here. But the interference is happening on the CCD camera. So the interference is happening between the diffracted field from the object and the reference. Are you okay with that? And then, as I said, you can block this beam over here and just monitor the intensity of the object. Then you get the EO, or the magnitude of EO. So the magnitude of EO and the phi O that you will calculate from here is going to give you the complex field of the object as recorded on the CCD plane. So then what do you do? If you want to find the phase and amplitude of the original object, you take that complex field and you backpropagate using one of the laws of Fresnel transform or transfer function and so on. Okay with that? So now that also means that you don't really care over here whether your phase is wrapped or unwrapped. Okay, because that is not giving you the exact, say, height profile or actual phase profile of the object. So here the phase can be wrapped. It doesn't matter. Because anyways, you're going to use that complex number to backpropagate. When you backpropagate and then you get the complex field at the object plane, that's where you need to do the unwrapping of the phase. Does that make sense? So there is no need to unwrap over here. The unwrapping needs to be done after backpropagation. Okay, here. Okay, so this is actually a very important thing. The point I want to mention is this was the first setup that was done by Yamaguchi's group in Tokyo or in Saitama. And then they actually, this is a standard, hologram that they recorded. There was a set of 4 holograms. I've just taken, one of the pictures. But now, after that, people became clever. People started thinking, oh, if that can be done, maybe we can put different kinds of phase shifts, different numbers of phase shifts, and all kinds of ways to figure out the final phi O, right? And here is a whole list of different what are called phase shift algorithms that have come up over the years. All right. So this case over here is the one that we just looked at, right? The 0, pi over 2, pi, 3 pi over 2. But that doesn't mean that's the only one. As you can see here, okay, you can have three. Three are enough. So you can have like minus alpha, 0, and plus alpha. Okay, then how do you find out the phase? Well, I mean, these, as you can see, there are, it's more complicated expressions, but it can be, it's just playing out with the trigonometry, right? So, okay, you can solve it. Then some people did, like 4-step, like minus 3 alpha over 2, minus alpha over 2, alpha over 2, 3 alpha over 2. Again, there is another set of complicated formulas. Some other people did something else in 5 steps. This is another formula. As you do, of course, more number of steps, you get more accurate results because, there is less and less contributions from noise, as it turns out. But okay, the basic one is this 4-step one, or 3-step, whatever you want to call it. I call it 4-step. Or the bare minimum you want is this 3-step.
Is the 3 pi by 2 equivalent to minus pi by 2?
Yeah, the same. Because it's 2 pi. 2 pi minus 3 pi over 2 is minus pi over 2.
We engineer phase monitor. The device is built.
Yeah. So the thing is, so you have to do this phase shift, right? You have to do the phase shift. So how do you do the phase shift is the question, right? So how do people do the phase shift? Well, typically they have a piezoelectric mirror. All right, so where is the piezoelectric mirror placed? That's the next question. So the piezoelectric mirror is replacing this mirror. So that mirror, okay, I mean here in schematic diagram is drawn phase shifter and then mirror. That's not what is done in practice. In practice, there's no extra phase shifter, but you have this mirror, but that mirror is mounted on a piezo device. So the piezo device is moved. Okay, now piezo device can be moved by electrical voltage, and then it can be moved by very precise amounts. And how much are you trying to move that? You're trying to move that by, like 0.5 microns, something like that. Because, to offer pi over 2 phase shift, pi over 2 phase shift corresponds to a movement of like lambda over, really lambda over 8. Because, the light kind of comes and reflects back. So, the total phase shift of the light is 2 times, the actual displacement of the piezo mirror. So you're talking about motions in the order of like 0.1 micron, something like that. And those kinds of motion can be done with these piezo mirrors. Right? Why such small numbers? Because the piezoelectric effect, the piezoelectric coefficients are usually very small. So if you apply like 10 volts, 20 volts, you can make the piezo mirror move by that kind of amount, like 100 nanometers to 1 micron and so on. So that's what is done. So now the next question is, so is that a worthwhile thing to do? Okay, so in order to do this, you need to buy a piezo mirror, right? You need to buy a piezo mirror, you need to buy a voltage source, right? I mean, and bias the piezo mirror. So that costs some money. Yeah, you can do that too. That is also not very cheap. You need to have a special light modulator. Yeah, so the thing is, what is cheaper? That's the bottom line. What is cheaper? Uh, Piezo mirrors have, I mean, they're not that expensive, but still, they're like $200, $300, $500, something like that. You need to buy it.
We use some kind of phase objective.
You have to have a very calibrated phase object. Yeah, right. And that phase object has to maybe double, triple. Yeah, I mean, you need to put in phase object that gives like pi over 2 or something close to that, and then put 2 of them to give double the phase. So, yeah, you can do that. But here was our solution to this. Remember, I talked about this business of these higher orders, right? And we said that if you have higher orders, the phase is automatically shifted by pi over 2 between the respective orders. So maybe we could use that. So in our experiment, that's actually kind of what we did. Okay, so in this particular experiment, this was just a tryout. This was just a tryout first. So we started from a laser source, and then we had the laser source really do a couple of things. We actually wanted that laser source to be, this particular laser source to deform the object. That's what we are trying to do. Okay. So what was our object? So yeah, so what was our object? Very simple. It was a CD, like a CD disk. So we use this laser to heat up the CD disk. All right, then it will, get some curvature and so on. So it's a distorted object. But the actual metrologic laser is this one. Okay, so this laser comes here, reflects from the displacement of the distorted object, and the other part of it goes straight over here, and then they interfere, form a hologram, and the first thing, of course, you see are the two regular orders, which are called the Bragg orders, and you also see some of these higher orders. That's the first thing you want to see, that there are higher orders. So the next thing that we did, again, now it comes to some more, calculated analysis. You need to figure out, if you write a grating inside this material, now you're reading it at the same time with light from the reference and with light from the displaced object, then what kinds of diffracted orders do you get? So this is a little bit of calculation. I don't want to get into details, but you can find out one at a time. You have a grating written inside. This is the grating inside the material, like lithium niobate crystal. You're reading it out with a reading beam in this direction, another reading beam in that direction. And each one of them are going to produce their respective diffracted orders. Each of those diffracted orders, have some complex value, complex amplitude, phase, amplitude, and so on. And these J0, J minus ones have really come from, the results of Raman diffraction in multiple orders. When you have Raman diffraction, the amplitude of the diffracted orders go according to the Bessel function. So anyway, so you add up all of these together. There's a whole bunch of calculations. Forget about that. But here is the final answer. The final answer is, okay, if you did monitor the intensities of all these different lights, okay, diffracted orders, and if you wanted to find out the phase, okay, the unknown phase, after a lot of calculations, the unknown phase, C, can be expressed in terms of the intensities of the different diffracted orders, some Bessel coefficients, which also depends upon the modulation depth of the grating, and that's pretty much it. So there, from this, you can actually find out the unknown phase. So what have we done here? Here we have automatically, put in the effect of phase shift by utilizing the fact that different diffracted orders come out in different phases. So I did not need any piezo transducer, right? Of course, I needed a crystal. Crystal is $1,000 or $3,000. Piezo transducer is $500. Okay, it's a compromise. But you can choose. But this is another way to do it. This way, you don't have to keep moving the voltage up and down and so on and so forth. Does this make sense? So anything that so these are topics of research, actually. This is still not complete. These are topics of research. Still work going on with some of my students on this. Why? Because again, as I'll tell you, so here, guess what? I have assumed that inside this material, the grating written has the same modulation depth, which is not true. Remember, we just talked about it yesterday. When you start writing the grating, even transmission grating, when you start writing, inside the bulk of the material, the modulation depth is still not the same. So you need to do more careful analysis and so on. So these are some of the examples that I had. Okay. The last thing I wanted to actually show before the break, and I don't know when is the break or what was that? 4. Okay. Okay. So the last thing I wanted to show is, remember we were talking about, and some of you were talking about before, of these Moray patterns? Okay, so here is an example of how you can use Moray patterns to do the same kind of thing, okay, namely uh, interferometry, right? Okay. Are you okay with this? So now this actually was a work done by one of my students, Hyun Gyo, and this was our master's thesis. But this is kind of new work actually. This is like 1.5 years old. So, and she actually received some student paper award in the Optica, digital holography meeting. So okay, the principle. Let's just talk about the principle. It's very easy. Principle is very easy. Um, of course, you know that. I mean, this is the part of the talk. Yes, I mean there are all these different methods to figure out, the distortion, right, or the deformation of an object. I mean, you have, contact type measurements where you can find out the deformation or, find out the actual profile of an object, like a profilometer, right? Or you have non-contact type. The non-contact type, certainly holographic methods is one. Holographic methods, yes, has the advantage. Of course, we are talking holography, but the disadvantage is you have to use a coherent light source, very sensitive to vibration. Uh, Certainly, noise, speckle is another thing, and so on and so forth. And there are other kinds of techniques. There are computer stereoscopic vision techniques. They're relatively simple, but then they also have disadvantages and so on. So the thing is, can you use something simple like Moire patterns to do that? And the answer is yes. I mean, it's very straightforward. So this Moire patterns is also in the same area as structured light. So in order to generate Moire patterns, you need to generate structured light, right? The same kind of thing that Dr. Nischel was talking about, these mosquito nets, okay? Mosquito nets is not structured light, but the light that's, transmitted through the mosquito net is structured light, right? So that's one way of generating Moire patterns. You can also see Moire patterns if you're walking past a fence, because fence is a periodic object. You see Moire patterns. See, I would not wear this shirt to appear on TV, then I would see Moire patterns, right? You see Moire patterns. That's why those TV guys never wear check shirts, no, or striped shirts, just regular shirts. All right. Again, where do those Moire patterns come from? Those Moire patterns come from the superposition of really two periodic intensities. One is the intensity of this check shirt or striped shirt. The other one is the pixels on the TV screen. Okay. Now, I might like to point out for the same reason, okay, if you actually record any kind of interference pattern on your CCD camera, guess what? If the period is, small, you'll see Moire patterns. And so you are not going to get a good recording. And we have seen that. And we have a paper on how to get rid of Moire patterns when you're recording a periodic pattern on a CCD camera. So you have to think about that as well. Okay. And in fact, as it turns out, we found out that you could eliminate Moire patterns by strobing the laser light. By putting a pulsed laser, you can get rid of the Moire patterns. Okay, so this structured light is a big thing these days, right? I mean, all gaming, everything, you have structured light. Why? Because it's very cheap, right? I mean, you put a structured light, like a whole bunch of these things, right? And then the light that's reflected or scattered, if you just view from a camera, as soon as the light is distorted, your pattern is distorted, you know the object has moved. And you know exactly how much the object has moved. So this is behind every gaming interactive gaming, technique that's used these days. So why not actually try to use this? So generate structured light and then make it fall on an object, get the reflected light back, and then superpose it on the original light. Then you get a Moire pattern, then analyze electronically, well record it, and analyze that Moire pattern and find out the distortion. Does that make sense? Very simple. Okay. Now, this Moire business, okay, I mean, Moire is like a beat pattern, but beat pattern is, from incoherent light fringes, really. So that's when you get Moire pattern. But one of the things I wanted to say is, let me just move on a little bit here. So if you had a reference structured light, if you had a reference structured light and if you had a deformed structured light, right? You want to compare the two. That's essentially what you're doing. When you're comparing these two, okay, you can, how do you compare two things? You can subtract, right? That's one way of comparison. What other things can you do? Maybe sometimes you can even multiply the two, okay? If you multiply the two, you can also find out the difference. A simple example, 2 times 2 is 4, 2 times 3 is 6. So if I multiply these two numbers by 2, and if I see a difference, okay, then I know the two numbers are different. It's as silly as that, right? But the reason I bring that up is because if mathematically I have two signals, so to speak, say U1 and U2, if I want to find out the difference between them, I could subtract the two, I could even add the two, I could multiply the two. As long as after I do that, I do the exact spectral analysis, then I'm good. All right? But finally, what do I want? I want the difference between these two phases. Make sense? Guess what I'll use for that? My phase shifting. Because this phase shifting I can do electronically on the computer. Okay? In order to find the unknown phase phi, I can shift the phi 0 by 3 steps, because all it needs is, I'll generate another pattern with the same thing, except phi 0 plus pi over 2 plus pi plus 3 pi over 2. And then I multiply or add, subtract these two things, and then I find some kind of a signal and I do some signal processing, and then from there I find the final answer. Okay, so that's actually what is done. The goal is to find the phase difference, phi minus phi 0. So as I said, you can add two things together. This is the Fourier transform, and this is the Morey pattern from the Fourier transform. You want to find this coefficient or this component, the cosine of phi minus phi 0, which you can find by shifting the phi 0 by 3 successive phases. So I'm not going to get into the details of that, but I'll just give you the final result. So this is again the essential equation that we use to find out the delta phi. And I'll give you the shape. Well, this is the same thing about phase unwrapping, because you have to do phase unwrapping here as well. Right? Now, one thing I'd like to point out here, the phase we are finding here, okay, the phase is the phase on the detector, right? So previously, remember we said, okay, we found out the phase at the detector, but then we had to back propagate it, okay, to the object. Here, this is all incoherent light. So what do we do here? Here, we image the object on the camera, all right? On an icon, really an Nikon camera, we image it. And we image the object that is distorted also on the Nikon camera. So we are already at the image plane. An image plane is a replica of the object plane. So therefore, any phase we find by this image processing is on the image plane, which corresponds to the object. You okay with this concept? So you don't have to do any back propagation. Just take your camera. That's what my student did. She had a Nikon camera, took the pictures, and that's it, and processed that. So this was the experiment that was set up. Okay, so the experiment was set up again with like a kind of Max Zender-ish kind of arrangement, not needed, but it was just done for simplicity. And then again, our favorite, Newport logo. That's our trial thing. So this Newport logo again was scanned with, as you can see, these fringes. Now, one thing, this is the simplest kind of fringe, right? That's just straight. Okay. You can change the angle. Okay. If you change the angle, sometimes you'll get better resolution, less resolution. It just depends on how much of the light is distorted when it goes against, these cracks or, the dents over there, right? If you did a more complicated pattern, okay, if you did a checkerboard pattern, you'd get more information. So that's more of a structured light. So you can improve on this, right? There's a lot of scope to improve. But this was just a demonstration. This is really the first demonstration of how you can use these Morey patterns. Okay, so all of that was done. Then, of course, once again, the period of the fringes was found and the phase was found, and 4 successive phase shifts were added or were applied. And then the moire patterns were found, and from there we found the phase. And once we found, so I'll leave out all the signal processing and so on. But finally, everything said and done, this was the wrapped phase from the Newport logo. And when it was unwrapped, this is how it looks like. Okay, that's the exact shape of the Newport logo. And of course, this is the first experiments that was done. So you want to verify it against standard techniques. So what did we do? Well, we took this, cross section or, line scan and compared it with that of a profilometer, right? So if you do that, and there is some business of angle and so on because there was an obliquity factor, but those I'm not getting details. But if you actually, finally go past all this calibration and so on and so forth, business is horizontal calibration, vertical calibration. This is the final 3D image, okay? And then this is a line scan, okay, along that line. And this is a line scan using the, kind of optical microscope, a KN's VR5000. And you're going to find out that these depths over here are exactly the same as this. That was the point. And they're typically in the order of about 100 microns, particularly. Are you okay with this technique? So this is a very simple technique, actually. Advantage, again, is incoherent light. And, how did we generate this pattern? Again, very simple. Okay, all we did was have one overhead projector or that, this kind of projector. That's all is needed. Generate pattern on the computer screen, projects from there and falls on your test object. Okay. Disadvantage, you cannot get to very small stuff. I mean, we did as good as we could, as you can see. But again, these are very illustrative experiments in a university lab because it costs nothing, as you can see. But the thing is, you have to think of these simple things. That's the main thing. You have to think, don't think complicated, think simple. Now, this same principle, by the way, was also applied to an application. What is a good application of this? Additive manufacturing, heard of that? Additive manufacturing. Everything is being additively manufactured. That means, you take a bunch of, plastics, you mold it to a toy. You take a bunch of metal beads, you melt them, and you deposit them layer by layer, and you make a part of, airplane or car or whatever. There's a lot of airplane parts being made that way. A lot of airplane engines. Don't be frightened. Okay, they work. Okay, it's not that the particles are flying apart. They're flying millions and millions of miles. But that's how they are being made. So when you are trying to make these metallic, say, additive manufacturing parts, one of the things you want to see is how smooth the surface is, right? Of course, you want to find that out. So in order to test the smoothness of the surface, guess what you would like to do? You would like to get a surface profile, okay? How would you get a surface profile? Well, use some kind of, holographic scheme. I mean, you can use just regular holography. In this case, we tried to see how good our method was of this moire pattern to see that. And as it turned out, yeah, I mean, this is kind of the typical 2D, as you can see the phase map of the surface. The phase corresponds to the height. And we actually checked that these actually correspond really to the expected roughness you would get. Because what you do in this metallic additive manufacturing, you take small beads, a whole bunch of bed of beads, and then you melt them with a laser beam. So you kind of go line by line. You melt them, and when you melt them, they melt, and then they freeze, and they form layer by layer of the surface. And what is important in this is actually what kind of laser pattern you need to melt that metal. That's where the art is. We didn't do that, of course. So you have to have a certain laser with a certain cross section, or you have to design some diffractive optic element to make a certain cross section so that the laser effectively melts the metal so that it can freeze immediately after. Okay, and as it turns out, the laser beam, there was a whole bunch of people working on this. It has to have some kind of a cross shape. for whatever reason. I mean, that all comes from metallurgy, of course, and material science. So this is an application. This has been later on also used to measure or calibrate, surfaces, for instance, concavity of surfaces. So, like you are making a lens, right? If you want to measure how uniform the ellipticity or the curvature of the surface is of the lens, this is a very useful technique. And we have tried it out, actually. That's not in this paper, that was in a follow-up paper. You can also find that. Just Google my name and write down, applied optics and Moray patterns. You'll find 2 or 3 papers. So that this was also applied to, thick lenses to see how the quality of the thick lenses was. And there was, again, a very interesting, calculation, because as it turned out, these Moray fringes, of course, will now look like a chirp pattern, because as the shape is changing, the curvature is changing, the distance between successive Moray patterns will become smaller and smaller and smaller. Does that make sense? I might have actually a copy of that reprint of the paper. If I do, I'll show it to you. And after that, we'll take a break. The other thing I also said, I didn't want to talk about it. Maybe tomorrow, if I have time, I'll talk about it. Has to do with how you can use the correlation. How you can use the correlation to compare two holograms and thus compare the nature of the 2D object or 3D objects. So this is the applied optics paper. Let me see if I have. This is the same experiment, the first one. The Newport logo. But the next one, I think here would be, no, this one doesn't have it. I think there's another. Here, okay. Just came out this year. Here, use of structured light in 3D reconstruction of transparent objects. So here you'll see that we are actually doing the same thing, but we are testing it on a surface like this. This is like a thick lens, a thick plano-convex lens. You can do it for any kind of shapes of lenses as well. But the main thing you see, the Moray patterns, they are not uniformly spaced because of the quadratic nature of the surface. But now you have to do some work. I'm sorry, generated by SLM, correct, yeah.
It's like a zone plate, but in a
Yeah.
cylindrical configuration.
Right, yeah. So we could do it with an SLM. This particular one, again, the SLM was this, the overhead projector. That's an SLM. That's it, literally what was used. There was a spare overhead projector. Again, generate the pattern, put it there. So that's the SLM. So we're really very simple. So here, once again, you see the different curvatures of the surfaces, how you calculate that, and then certainly the results work out very well. Otherwise, why would we show it? So this is typically how the Moray pattern would look like, in the actual experiment. The periods are different. And then you do the period. This one? Yeah, this one, we just drew it, by shining part of the light over the lens and part through the lens.
Yes.
So they're big stripes of light. So make part of it go above the lens and part of it through the lens. That's it. So that's the only difference. So you see, very simple. This was the thick lens. Anyways, so just to give you an idea, so this is so we had to measure, this lens, what was the height, what was the width, and that exactly compares with what we got here using the Moray pattern technique. And this was a case of some other cylindrical lens, but all of them worked. Anyways, bottom line, it was to show the use of Moray patterns to do really evaluation of surfaces. Any questions here? You okay? All right, then maybe, I think it's probably close to break time. Then after that, someone else will, I think, give a little talk, right? Seminar? Right, and the other thing I would like to say, maybe after the talk, I would just like to keep 10 minutes or so to talk about, the progress with your homework. And I wanted to add on to the fact that I want you to put in a reference beam and then record the interference pattern. And then, do the FFT or whatever you want to do, okay, to isolate one of the side bands and then back propagate or forward propagate and recover your original Gaussian. But we'll talk more about that after that seminar. Okay. Any questions? Let me know. I will also send some of these to you. Hope you find it of interest. So I think you've learned about different ways of doing, metrology.
Any shortcomings or constraints of using wave patterns for analysis?
The only things we found was the fineness of the Morey patterns in our case.
Yes, that is definitely one, except that.
Except that, no.
Okay.
The analysis can get harder, right? The analysis can get harder, yes. So you have to really work on, the inverse problem. The inverse problem was not easy because you are getting a certain pattern, okay? So you know all the phase from this pattern and so on. Now you have to map it to the, shape, the actual circle.
Kindly unmute. उसमें भी डाला हूँ ना, शेयर कर दीजिएगा तो हो जाएगा। ये
ये बंद कर दीजिए।
ठीक है ना?
Yeah, okay. I can resume it then. Okay, yeah. So I was talking about that the development of the terahertz integrated topological circuits. So before when we develop any technology, it is very important to understand the problem. That what are the problem and what are the stuff that we are going to challenge and solve. What are the roadblocks? So in the terahertz, why we wanted to study. First, I wanted to highlight the key applications, which is extremely important nowadays. So the first one comes the high-speed wireless communications, and I will show in the details that why and how terahertz is going to help in order to realize the 6G communications because the carrier frequencies are keep ramping up. We need a high bandwidth and the high data rate. Similarly, for the sensing, like as we know that the terahertz wavelengths are high, large in the nature, and there are several biomolecules that fingerprint lies in the terahertz regime. So it is a very promising candidate for the sensing applications. Now related with the concept that we have here imaging and the 3D holography, and we all know that from the sci-fi movie that like we have seen in Iron Man and all that digital twinning is happening for all the biological objects. But if we have so, how we can transmit wireless from one place to another place? So for that we need a high-speed data communications also. And terahertz I think that the terahertz is extremely important if you wanted to twin a full body because using optical light you cannot do so because you need to scan the full body. For that you need devices using the wave which does not harm our tissues and the wavelengths are also high in the nature. It is a good candidate for even the 3D holography also. And from the fundamental point of view, like if you wanted to study the 2D materials and study the charge carrier dynamics, the terahertz comes into a very handy. And I'll just skip that. That okay, everybody knows that 6G is going to revolutionize the world because the digital twinning is happening. It is going to merge the physical barrier between physical and the biological world, and all this low carbon footprint and artificial intelligence also going to come into the picture. This will come up with like industrial 5.0 revolution, and this is the reason that all the big players from the USA, Europe, and intense industry academia collaborations are happening. We have to remind that because, as like Prof also mentioned, that as the worlds are keep progressing, multidisciplinary, interdisciplinary things comes into the picture. So one person with one single-handed expertise are not going to solve big disruptive applications. That's why so 6 is one of the example where the guy from the physics photonics having the photonics expertise, computer science having the artificial intelligence expertise, electrical engineering, and everybody has to come into the picture. And from also the industrial people also have to come into the picture. And this is like a big motivation because like if you look at the market size and the jobs perspective, it indeed has fertile playground. So this graph provides background that how things are evolving. So if you look at this curve, so we like the first generation, second generation, third generation mobile communications, and the peak data rate has been retained. So 4G like talks about that 1 Gbps speed will be there. Right now we are witnessing in the era of 2020 plus Then the 5G started to roll out. Obviously, India, we are still far away. And the carrier frequency that we see, that 100 gigahertz, which is keep increasing with the generations are keep ramping up. Once we go in the 6G, the carrier frequency will start to lie in the terahertz regime. And the terahertz regimes are unique in the electromagnetic spectrum because it comes between the electronics and the photonics. So which means both the world has to come together to develop whatever the missing part is there in terahertz. For example, the photonics people enjoy that they have the laser, they have the modulator, they have every like a single light modulator to do the beamforming, to do holography, but terahertz does not have that kind of concept. So obviously, the metamaterial link community came into the picture in order to do all this, provide all this vacancy. Similarly, electronics has the power amplifier, transistors, what we are seeing, the current computers and all. Then terahertz also does not have that. So both would have to come together to fill the gap because if you wanted to realize all these disruptive applications. So that's why this field has lots of opportunity in terms of application as well as research question. So one of the problems that we are targeting, which is one of the bold problems that we are targeting to address is like we wanted to develop a chip that use terahertz as a carrier frequency to transport data on chip itself. So for example, right now our clocking frequency in the computer operates at 2.4 gigahertz. 2.4, and now I'm talking about 100 gigahertz carrier frequencies. Imagine that our transistor is not going to operate. It will provide huge heating. Why it is happening so? Because they use copper interconnects. So electrical interconnects cannot support terahertz wave. It will provide huge ohmic loss. So which means some novel mechanism, some novel disruptive applications, some novel solution are required. And so that's why we came up with the concept of topological devices. Why silicon? Because we don't want to disrupt the existing technology. So for example, silicon is like low propagation loss, which provides large manufacturing with the CMOS-based devices. And what we are offering is like the negligible bending loss that provides the miniaturization, which helps the devices to be small and small, and active tunability is like something that provides the functionality. So if you look at the history, whenever any technological revolution happens, who came up with the solution? Obviously, the physics person came up with the solution. So here also the kind of solution that we were seeking that okay, we need to get rid of the copper interconnect. We cannot use optical interconnect because it's too expensive and all. Then in 2016, the gentleman from the David Hollis Halden, which got the Nobel Prize for the topological phase of light and matter. Which says that by doing some engineering, I'll talk about that, what that engineering, you can get a robust transport of electrons. So be careful that I'm talking about electrons here, even at the sharp bend. So here, this schematic just shows that the electrons are being transported even at the presence of sharp bends, yeah, any defects, whatever the things can be there, the transport is not going to be get disrupted. So this was the big motivation for us. And then we thought, okay, this is for electron. Can we bring this concept into the photonics? Then we did and found out that this behavior, because electron by definition is fermion, light by definition is bosonic in nature. So both are fundamentally different. So can this property comes into the picture? The answer is yes, because this property of topological is not because of bosonic and fermionic nature. It is coming because of the wave character of electron. And now, okay, electron is wave, and this photon is all about the electromagnetic waves. So then we have the answer, and so we have the motivation. Then we came up with that, okay, we can indeed bring this concept into the photonics, and indeed we can realize a robust transport of light. So here this schematic signifies that, like for example, terahertz is coming. You can imagine that this is a chip, and this whole are something which I'll talk about that, which is a part of engineering, which dictates this robust propagation. So here you can see that indeed having a sharp bends like 60 degree and 120 degree of bend, the light is not reflecting back. It's keep nicely propagating and then going from here and the other end. Then once the platform was set, then we were ready to come up with our proposal and we put a very bold proposal in the Singapore Prime Minister office and then say that, okay, we wanted to develop a terahertz wireless link where we will develop an on-chip transmitter where everything will be a chip scale, then on-chip receiver, then we will send even 100 Gbps of the data. The distance will be small, and the reason for that because right now we don't have high power terahertz sources. So we had lots of rebuttal with the Prime Minister office, and then finally they bought our idea and then funded us. So then we started our journey in 2021. So, like as I mentioned, the journey from topological insulator to photonics is not very trivial because, for example, if you guys have seen or saw some videos that the Nobel Prize came in for the topological insulator, which is like electronics based. Then what photonics people did, they designed another in photonics. This is called quantum Hall effect. The first was the quantum Hall effect. Second was spin Hall effect. So in electronics, quantum spin Hall effect was shown by Kane in 2007 from the Stanford University. Then in 2010, the photonics community picked and then showed the corresponding spin Hall effect. So one of the questions was that people always ask why you guys are mimicking. The electronics community always ask to the photonic community why you guys are keep mimicking us. Can you guys won't come up with something new? The answer is that yes, photonics offers something more. Because for example, in electronics, the band structures are fixed. Because the electronic position, crystal band gaps are fixed. So we cannot do lots of engineering of the Hamiltonian. But in photonics, we can do whatever we want. So because of that, we can study this Cloquet phase and nonlinear convection photonics. Maybe these terms are not familiar. Maybe we can. I will explain it a bit later, but not now. So this just to tell us that topological photonics can provide much ahead, and it is extremely important for fundamental study as well, not only for technological point of view. Then, okay, so now I'm going to talk about what are my building blocks, how we are building the stuff. So everybody has seen the graphene structure. The graphene is basically like hexagonal lattice where carbon single bond, double bond, alternatively arranged. Yeah. So you can understand these things similar to graphene. So where the black represents our air hole, so here we have a silicon cube, and where the holes has been drilled. So you can notice that the bigger triangle, smaller triangle, bigger triangle, smaller triangle, alternatively arrange each other. So this is equivalent to like single bond, double bond. So what it does, having these things, what it does. So let's suppose if the triangular sides are all identical, then there will be a Dirac point. And if we break the inversion symmetry by changing this triangle, then there will be a photonic band gap which is opening at the K value and the K prime value, similar to like graphene. And this is extremely important because whatever things are going to happen is going to happen within this region. And this guys provides the robust transport. How? Then the smart engineering comes into the picture. So you can see that, okay, we can start from identical triangle, then break the triangle in such a way that both are mirror image of each other. So what it does, having mirror image of each other is basically like providing a different sort of dispersions. So if we wanted to go in detail, we will go in detail. But what this dispersion signifies that, so let's suppose if you are arranging AB type of where let's suppose bigger triangles are facing each other, so it will have this kind of dispersion. The group velocity is the d omega by dk. So let's suppose it has rightward propagation, and if we make arrange the lattice in such a way that smaller triangles are facing each other, then it will be backward propagation in nature. And I have to remind you that these things are robust. Even though if we mix these two, this propagation is not going to hamper. So once the waves are locked in this direction, it will be in this direction only. And in this domain, if the waves are locked, it will always move in this direction. It's not going to back and flat. So taking this as an advantage, and why these things are happening. So like Prof was mentioning in the talk also that the phase is extremely important. So here also the robust transport that is happening at this domain is guided by the vortex that exists in the phase profile. So for example, here you can see that this particular unit cell has clockwise rotation, this has anti-clockwise rotation. So naturally, at the domain wall, they will have a tendency to allow the wave to go in forward direction. If we flip it, obviously it will ask the wave to move in the opposite direction. So this phase vortex is extremely important, and I think one of the basics and core to realize the robust transport. So phase is like always important. Then what I said, okay, the robust transports are happening. Then I have to show that okay, indeed it is happening. So here is the proper example. So you can see that we have 18 bands and the waves are nicely transporting. Here, if we take any photonic crystal, you can see when two bands, the lights get destroyed, it's not able to transporting from one place to another place. And indeed, this is the reflection spectra where this is the real chip that we fabricated, and we send the light from here and record it from here. And you can see that the straight and the bends have nearly identical transport property. So once the transport property is set, then where the communications are happening, we have to show that importance as well. So let me play this video that, and I will edit this video again. So in the background, what you are seeing is a high definition 4K video, which is playing via this chip. So you can see that the several bands are there. We are sending the video via this chip. We purposely make one wireless window here. So terahertz is transparent to paper. So that's why when paper went, nothing happened. But when metal came, the video gets blocked, and it will retrieve back again. So this shows that. So this is live 4K video transmissions are happening, and for that you need ultra high speed. So for example, we have achieved like 11 Gbps of the speed in order to see this. Well, let me narrate it again because so for example, we have a chip and we have the transmitter which is loading the background videos, packing it onto the chip, and it is propagating. And then we have some wireless channel. Then to showcase that indeed it is happening via terahertz, we put paper. The terahertz is transparent, nothing happened. But if you put the metal, it disrupted the channel. And then this shows that, okay, so now the performance of my device is working well. Now the next big challenges was that this big guy that you see that the transmitter, receiver, everything is outside. I have to bring everything on the chip. So that is one of the challenge that we had to solve. Second challenge that we had to solve that the speed was 11 Gbps only. In 6G, we are talking about 1000 Gbps, which means 1 terabits per second. How that can be done? Till 1 by 100 times we are slow down. Then the answer is that this limitations is coming because of the bandwidth of this chip is very low. And how we can enhance the bandwidth is like the reflective index contrast comes into the picture. So that bandwidth engineering I will skip now because I have to talk about the another functionality which is like the cavity. So far we have seen that only waves are transporting. So far so good. But if we want the other functionality, because integrated circuit does not mean the wave has to transport from one place to another place. So for example, like our phone has 4G and 5G both. If you're moving from 4G tower to 5G tower, it automatically detects itself. How it is detecting? Because there is a filter inside our phone which sends it to pick the frequency, one frequency, and sends it to another frequency. So all the functionality like filter, switching, even phase shifting and the modulator, who will do? For that, you have to come up with a cavity design, and they will do all this functionality. So only having the waveguiding does not make any sense. So then what we did is like, okay, we designed a cavity which looks like a closed path. So this is similar to like the whispering gallery cavity if you have seen. So traditional whispering gallery cavities are ring resonator. Why it is ring resonator? Because if any perturbation happens, then there will be back reflection. But here another advantage is that we can have a sharp bends thanks to the topology that it does not provide any back reflection. So that you can see that the waves are nicely transporting despite of having a sharp bends. And if the wave comes from this waveguide, then at the this dips represents the resonance frequency which is measured here. So these two dips are the whispering gallery resonance frequency. If you have seen that 2 pi n equal to n length of the whispering gallery resonator. So if we increase the size, then number of frequency will also increase. So for the timing, we just only chose the length such that we can have only 2 frequency. We don't want to do multiple frequency. So, and what I have to remind you that the quality factor of this is like 10 to the power 6, which was one of the highest reported value because of the low loss nature of this particular device that is offered by the topological photonics. So can we use this for any on-chip communication applications? The answer is yes. How we can do so? So the thing is that let's assume that okay, we can at input we can come up with two channel 1 and channel 2. So let's suppose we can take carrier frequency 330 in channel 1 and the another carrier frequency of 334. Both are spectrally far apart. And once we launch it, what will happen? It will go here and cavity will pick this guy because this is the resonance frequency of the cavity. As you can see here that the waves are coming and the cavity picked its resonance frequency and transport it to the another channel, which is here. And then the another carrier frequency, which is far away from the cavity resonance frequency, will nicely go here. So doesn't it act as like a filter, natural filter? And indeed, we saw that yes, so here the bandwidths are higher. We are able to show 40 Gbps of the data transport from this channel, and the high definition video from this channel because the bandwidth here was very limited. So to showcase that indeed these things are happening. Some of the guys help me to play one of the videos. I have to click it on this. Yeah, okay, that's it. Okay, so what you are seeing here is that okay, so we have taken the video in a very weird configuration. So what you are seeing that this chip is tilted in this direction, and we are sending this to data, and the video that you are seeing is the live high definition video which is playing via this channel. And we purposely made one wireless domain here because as we keep the metal, the videos are keep disrupting. But the 40 Gbps data which is transporting via this channel, nothing happened to that. So once again, if we came up with the paper, the video display does not get affected and nothing happened to this 40 Gbps data streaming as well. So this shows that okay, so yeah, this chip device can operate as demultiplexing functionalities, and further also if we can come up with purposely if you can destroy the 40 Gbps, nothing will happen to 1.5 whatever the HD video that's happening. So I can just skip these videos. Now the next concept comes. You can ask. Now you are showing everything happening on chip. But from 6G, we need to develop that things has to radiate out into the air. Then the concept of phase shifting comes into the picture. So, for example, you can see that this guy can help the electromagnetic wave to couple from air to chip. So, using the principle of reciprocity, it can also do the other way around also. But the single spikes won't be enough. So, we have to come up with a novel approach so that multiple spikes and the spacing and the length of the spikes are important because this will decide where the beam is going to be formed and we can actively do the steering. So this is important. The second approach we can also come up with that we can design some graded refractive index media because the wave when it's propagating in chip having the refractive index of silicon, but if it has to go to air, the refractive index is 1, so high impedance mismatch will be there. Then we have to come up with some graded refractive index concept so that the wave nicely can go and slowly can go out of from the chip, and then only we can realize the on-chip to off-chip devices. So these are some of our ongoing works, and we have shown that we can indeed get 100 Gbps of data speed over 5 meter of the distances. Now, like Prof was talking about the holography interferometry, and in all the interferometry, you have noticed that the path difference is important because that path difference can give you the phase difference. But here, it's not happening. Here you can see that we have the waves are coming and we are splitting it into two parts. So the top part is the wave is transporting the same geometrical length, like it will go. Bottom part also it is transporting the same geometrical length, but still once it combines, we can see an interference pattern. So this green color is like showing the interference pattern and the blue is like showing some delay. Why that is happening? From where the waves are getting this kind of phase differences, having identical path difference, then the concept of geometrical phase comes into the picture. I think in quantum mechanics you might have heard about the concept of geometrical phase. So that's one of the in-depth physics that we are studying, and we will show that this phase, whatever the things that we are coming at, is extremely sensitive, that even little bit of perturbation can provide lots of transparency, and we can have all this modulation functionality and all the black matter interactions that we can do. So yeah, so this was the completely on the on-chip part. The last part that I just wanted to touch upon, because this conference was on completely on the phase, how the phase can be harnessed to realize all these disruptive applications. So one of the recent concepts that is very hot and it can solve, literally I can tell you, the $1 million problem, which is like very configurable intelligent metasurfaces. So what it does is you can imagine that, okay, light is coming up. This has some metasurfaces. So this is the zoomed part shows that different size of silicon cubes are there. So which is like a phase gradient. So because of this phase gradient, the output beam can split in multiple ways. It can be a 1, it can be 2, it can be 3, depending on how the phase gradients are there. So what are the challenge, which is still an open problem, I'll tell you, that how we can achieve an active counterpart, which means that we want arbitrary shaping of this guy so that it has to be done actively. So let me tell that first what I mean by active. So imagine that, okay, we have multiple users where the light has to go, and these users are changing their position randomly. So this metasurface has to serve because they have to send the light to the corresponding user. How they can do so? So for that they have to change their spatial configuration, and then only they can do, because the angle of emergence depends on how the field gradients are. So for that, this metasurface has to connect it with some feedback loop, and then the concept of artificial intelligence comes into the picture. Then AI, what it can do. So for example, here you can see that the input pattern. So this dark spots are the user position. Then it will go to the neural network. This neural network is connected to the metasurface. It will ask metasurface to change this spatial configuration because your users has been moved away. You have to change your spatial configuration, then only your beam steering can be changed actively. So this is one of the theoretical study that we did. If anyone can do the corresponding experimental work and done the patent, I'm telling you, I think, I don't know, you guys will earn in billions, to be honest, because this is one of the big sell. If you look at the Samsung, Intel, even Apple, all the 5G, 6G players, and all the even the holographic community also, they all need this kind of intelligent metasurface, which gives the on-demand type of angle of emergence. So this is one of the active area of research. So I'll just quickly go to the underlying physics, how it happens basically. So it happens that the design principle is following that. Okay, so you can take the cube. So this is the cube size we have taken, like this square, and this thicknesses and all depends on what frequency you're operating. So for me, it was terahertz. You can translate this to into optical frequency. All these concepts are scalable in nature. And this is the transmittance. So what you have to keep in the mind that whenever you design your meta surface, you should not lose your transmission because that will change your intensity. First thing. Second thing is like you need to have full 2 pi phase gradient because then the concept of generalized Huygens, generalized Snell's law comes into the picture. The normal Snell's law says that if you have an interface, angle of emergence, then theta will come out, which depends on the refractive index. Generalized Snell's law says that if you have a phase gradient, not a simple interface, so depending on how phase gradients are there, your angle of emergence will be dictated by generalized Snell's law. So you have to design a unit cell which will give you full 2 pi phase coverage. So that's why then, so these are the library of simulation that we do where LX and LY mean all the geometrical parameters we capture because this will help us to select, okay, what are the LX and LY we should select that the transmission, first of all, does not get lost. So for example, we always select from this regime, we should not go to this regime because these are useless. Similarly, for the phase also, we always go in this region because that will provide the 2 pi phase gradient. And these are the informations are important for this neural network to operate. Because neural network will understand, okay, what I have to choose so that we can provide this kind of configuration, different configuration based on user demands. So these are the still active area of research that these people are doing, not only terahertz, even in the optical frequency as well. So I'll just conclude my talk that yeah, we have achieved the on-chip communications and where we came up with the 160 Gbps of the data, even though I showed only the 10 Gbps. And how we do so, because again, the artificial intelligence came into the picture. AI helped us to design a photonic crystal with a large bandwidth. Similarly, the integration of cavity helped us to get a filtering application. Then from on-chip to off-chip and the reconfigurable to then meta surface is something that we are doing for because we wanted the way to go out of the chip and we want on-demand control as well. And ultimately, all these things will help to lead us to develop the integrated circuitry, which after 5 to 10 years will be going to integrate with cell phone devices. Because right now, all you have 5G devices, and the 5G devices, I think all the things are same as 4G. Only couple of chips has been changed, and for that, the big companies are charging a lot from us. Similarly, the same thing is going to happen with the 6G as well because nobody does want to disrupt the existing technology. They just add on something and then come up with more. Yeah.
Thank you for a very nice question.
The meta surface they use that is apart from is different from this material like normal material or
The meta surface that I used is like it's a cube of silicons with having different LX and LY. So meta surface, as the name suggested, is like it's a engineered material. So you have to your target is fixed. You don't want to lose out your transmission. You want to achieve your 2 pi phase gradient. So that's why you just design LX and LY accordingly, and it will give you different board of engineering.
similar with meta material.
Similar with meta material, yeah. Meta material.
Explain a slow change like
Yes, yes,
getting it.
yes, exactly. Oh yeah, okay. So like Prof, these are the schematically like LX and LY we are changing. So we are asking the meta surface, this neural network, to talk to the meta material, and then asking them to change LX and LY such that it will give the beam according to the position of this user. So we have already simulated the whole library of LX and LY, which encoded the information of transmission and also encoded the information of phase. And like generalized Snell's law says that how you were arranging your vector surfaces. Based on that, your angle of emergence will be. So like here it is passive in nature. So for example, it can only give you 3 output beam. But if you want 2 beam and angle of emergence also, then this guy has to be changed. So that is one of the major roadblock that we are facing. Actively tuning. That's why I was asking even Prof also. Do we have any method so that we can change the phase actively? Let's suppose LX and NY are fixed, but we want this phase to be changed actively. So then only these things can be realized. Otherwise, this will be still in the dream. That's why these problems we told that these are the $1 billion problems to be solved.
Can you use them in case you are?
Yes, the MEMS actuator, MEMS and NEMS actuator. That is the one thing that we wanted to do. But one of the MEMS actuator is that first it is slow. The speeds are in the millisecond range. But that is the only way we think that could be done. So that is like our working, we are working on that one. And the second problem with the MEMS is they are the metallic nature.
You can try using this ferroelectric liquid crystals.
Yes. So
Liquid SLMs are very fast.
yeah, but I think that is very good for in the optical frequencies. I have to bring that into the terahertz. Yeah, liquid crystal people use it in terahertz. I know, but liquid crystal one of the problem is it can only provide on and off state, nothing in the intermediate. We need something that cover the full phase gradient, like full phase gradient.
You know, liquid crystals are available in full phase also.
Oh, they can.
Zero to 2 pi completely.
Oh, okay.
Because you can do it 0 to 2 pi. Only thing is that the moment you do 0 to 2 pi, then the speed is slow.
Yeah, that is.
But ferroelectric one which works in the binary mode. So either 0 or 2 pi.
Okay. That, I think
Then those are very fast.
okay. I think very few options are there active tuning for the phase gradient.
So better material with that ability.
Yeah, exactly. The active metamaterial in that regard is what people are looking for. Passive design is fine. Everybody has exploited the passive design, and we all know. Even the neural networks, all these things are ready. Just we need to get a configuration how to do active tuning.
Phase change.
Yes, GST and the VO2. For the phase change material, one of the things is like compatible. Second, it requires heating.
No, the photodetective materials also have that phase changing properties. But you have only mostly. Yes. If there is under, then you can.
Yeah. So how many states we can get in the like the crystalline to amorphous? There are some intermediate state also in the phase change material.
No.
So that we can get multiple only 2 states. Yeah.
No questions. I'll give you a big hat.
Maybe there are other things that comes from there. Talk about something unpleasant. Not to talk your mind's rest. I think.
Went into a different domain and now.
Yeah, now you're
Back to
saying.
the optical domain. Change of frequency.
I think what I'll do is,
Phase, domain, dimension, everything.
how can this be raised?
Yeah, he will remove,
So I can work on the, the whiteboard there.
screen को ऊपर कर देना. Computer control, you will control this. इसको भी off कर दो.
Yeah, I mean, I don't need anything. I just wanted to. Anyways, I know it's getting late, but just a couple of words on that homework. Okay, so once again, please draw a Gaussian beam, one-dimensional Gaussian beam with 10 micron. So whichever one you want to take, say 10 micron half width, but you need to sample it according to what you want. And then make sure the width of this one is about 1/4 maybe of the entire width. And then take the FFT. So you call the FFT program, take the FFT. FFT, so if you have this one, as I said, this total thing, if it's n, total number of points if it's n, and then this is like a delta x, like delta x. The total, span of this is n times delta x. So in the frequency space, when you take the FFT, each one of these little things here, this is going to be like 2 pi over n times delta x. Okay, and you're going to get, if you start with 1,000 point FFT, you're also going to get 1,000 point. When you take the FFT, start with 1,000 points there, you get 1,000 points here. But the resolution in the frequency domain here is 2 pi over n delta. So just try out, and then, just call the FFT program, and then draw the spectrum. And the spectrum will look like this. Spectrum will look like that. Okay, but try to draw the spectrum. Unless you draw it, you'll not have an idea of how it looks like. So vary, you can vary delta x, for instance, and then, see how many samples you need. And then you fit this one so that it's about, 1/4 about of that entire span. Draw that curve, do the FFT, then look at this one, how it looks like. See if this can be optimized. Maybe if this is too narrow, see if you can make it wider by playing around with the sampling and the points. But once you have that, after this, you have to do the FFT shift. So when you do the FFT shift, this whole thing, this part is going to move here, this part is going to move here, and then this is how it's going to look. How it should look. So this is the spectrum. This is the correct spectrum. Then you need to multiply that with the transfer function for propagation. Transfer function for propagation, okay. Someone said you didn't know that, okay, this is the transfer function for propagation. It is there in the notes. E to the j kx squared z over 2k0. That is the transfer function for propagation. K0 is 2 pi over lambda. Right? So that's the transfer function for propagation. I need to multiply this spectrum with that transfer function for propagation. Okay, before you multiply, try to see how this looks like. Now you cannot plot this because if you plot the magnitude, magnitude is 1. So that's the problem. So what you can plot to see how this can look like, maybe the real part. So if you plot the real part, what is the real part of this? What's the real part of e to the j theta? Cosine, right? Cosine. So it was not the cosine of kx squared z over 2k0. See, this cosine has a varying period because it's a kx squared. So it's like a chirp function. The chirp function plot, but you should plot it. Okay. You should plot this with the same value of delta kx that you have found from here because you have to multiply point by point. So when you plot this, how will it look like? So this cosine guy, cosine guy of course goes between +1, -1, right? So, but the period initially will be large and then the period will become smaller and smaller and smaller. Right? That's how it will look like. And you have to draw this. Unless you draw this, you don't know how it looks like. I mean, I can draw all I want, but you have to draw it on the computer to see how it. But you know how it's going to look like. Okay, so. But the reason why I say this, now let's see if I multiply this with this. Okay. One issue here is that, okay, this guy, I just took the cosine, yeah, the sine is similar. But then, actually, as it turns out, in this case, sine really doesn't matter. Cosine is good enough. But let's see, if you multiply this one with that one, so what should happen? So I'm going to draw it with a different color. Okay, I'm going to draw it with a different color if I can. So if I multiply this, okay, so if I multiply that one, see that function? That function looks like this. Right? Make sense? So point by point, if I multiply, what will happen to the blue curve? It's going to go down. Right? At least in this region. That's the main thing. So when the blue curve goes down, that's what you need to make sure. You're multiplying it so that the new blue curve, maybe it looks like this. Right? Narrower. So what do you mean? What does it mean if the blue curve is narrower? It means the spectrum has become narrower. If the spectrum has become narrower, now again, do the inverse procedure. You need to do the FFT shift and then take the inverse transform. If the spectrum is narrower, then in the space domain it will become wider. Right? So that's what you need to check. And as I tell everyone, every step has to be drawn because you see there is a picture here going along with it. So then that will give you an idea of how finally that looks like. And that's about it. So yeah. Is that okay? Okay. So keep doing it till, like this is say at z equals 0. Keep doing it till z equals zr. When z equals zr, what's going to happen? You know already that this is going to become y. By the way, the width you measure, this is peak. Peak is 1. Width is, the point where you have the 1 over e point of the beam. So that's the width. Okay, so here the width was taken as 10 microns. You'll see when you propagate z equals zr, okay, z equals zr, this height is going to go down and the width is going to be wider. That's what's going to happen. But now make sure, that's why I said start with about, Gaussian that occupies about quarter of this region, because then after it's expanded, okay, it will become wider. You don't want that edge to go over here and become non-zero. It should go down to zero. Otherwise, you'll see some reflection coming back and your net result will look like that. Hold it up. You don't want that. So that's why you want to keep it within bounds. So that's pretty much it, for that part of the problem. And then if you actually make this one more and more like a super Gaussian kind of thing, okay, the super Gaussian spectrum will be wider. So, okay, so this spectrum initially could be narrow, that's fine, which is actually good. But if you do super Gaussian, you're going to see that this spectrum will start to have this kind of oscillation. And then if you multiply it by this, go ahead and do the same thing, take the inverse transform. You're going to find that this curve is not going to be sharp. Okay, why is it not going to be sharp? Because when you take the spectrum, okay, the spectrum is something like this. Okay, but spectrum, when you're multiplying it by this kind of a function, see here is going down. So higher spatial frequencies are going down. So that means the sharp edges will no longer be that sharp. The sharp edges have higher spatial frequency. Right? Does it make sense? So that's why when you see that guy, the edges are going to become smoother. Okay. For some distance, you will see the initial peak will become a little bit higher, but then it will continue to go down, and then finally, it will start to look like a sinc function. But sinc function, you may not be able to get there because you start to see some reflections on the boundaries. But as long as you see, it has kind of gone down and have at least some evidence of ripples, that's good. So that's those three parts. Then the last part is, so you start with a Gaussian beam and it goes through a lens, so you need to do that. And you have already done the Gaussian propagating to the Rayleigh range in the first part of the problem. So you know what the complex field is. Okay, you are only plotting the intensity, okay, but in your data, you have the complex field. So if you have that complex field, say, let me just write that as G at the Rayleigh range, GR, then that needs to be multiplied with the lens phase term. The lens provides the phase In my notation, it's just e to the j k0 x squared plus y squared over 2f. Right? And in this case, the f, you're going to take it to be equal to zeta. Right? So then what you're going to find, so this is the expression for a converging mass. Okay? Then what you find, you multiply it, okay, and then you start propagating. When you multiply it with this phase, if you plot the magnitude is still the same, right? Because this is a complex number. But then you start to propagate. When you start to propagate, you'll see that this is going to converge, and it will get back to the same width, like W0. You'll get back to the same width, W0 at a distance f, which is equal to zeta. Right? Makes sense? So that's that part of the problem. So here what you have done, you have focused the Gaussian beam. Now the other part that I was going to add to this is, so you have the Gaussian beam, okay, let it propagate. Let the Gaussian beam propagate. I have to say Z equals ZR, because you already have that. But now, on top of that, introduce a plane wave traveling at an angle. Introduce a plane wave traveling at an angle. So all you need to do is whatever complex field you have for the Gaussian, like this GR, to that you can add some AR times e to the minus jk0 sine theta times say x. Right? Because that determines the angle at which this is going. And that's all that is needed. Okay? So then, say let's suppose that is your detector. That's where you are detecting. That's your recording of the hologram. So what does the hologram record? Is the intensity pattern, which is also equal to what, in the literature is called the hologram function, H. I don't like that, but I think holograms. Okay, that's the hologram function, right? So now when you have this hologram, are you okay up to this point?
Yes.
Okay, once you have the hologram, guess what you have to do? Take the FFT of the hologram. What will happen when you take the FFT of the hologram? When you take the FFT of the hologram, you're going to get some patch of, non-zero values there. And if the displacement is along X, you'll have another patch here, another patch there. And the separation will depend upon the theta. Are you okay up to that point? Now, here you need to use your imagination and crop one of them, whichever one, okay, or both, because one corresponds to the virtual image, one the real image. Virtual image, you need to back propagate. Real image, you need to forward propagate. Okay, but before you propagate, at the end, what you need to do is you need to center it. You need to center it. Why do you need to center it? Anyone? Actually, Prof, why would you like to center it? Remember this axis. This axis is the frequency axis, kx. So after you crop, why do you need to center it? What kind of information is there in the fact that this is not in the center, but it is shifted? What is this distance over here equal to? We just have that expression over here. What does this? The theta, the angle. The angle decreases, the separation decreases. All that this one is, this separation is really like k equals k0 sine theta. That's the separation. Is everyone okay with that? As you decrease theta, the separation decreases. So the choice of theta is up to you, and you have to work on it because it depends upon the spectrum spread of the spectrum. If theta is too small, all of them will be on top of each other. That's not good.
Theta is 0.
Inline, right? When theta is correct. It's inline hologram. You could even try that and see what happens. That's fine. But, you try the case where theta is non-zero, like, 1, 2, 3, 4 degrees. So what should theta be? Theta should be such that this separation is more than the spectral spreads of the Gaussian. And the Gaussian spectral spread, the initial width of the Gaussian. You know how this Gaussian spectrum looks like after distance ZR of propagation. So you know its spectrum. Right? So you really know everything. You know that. Okay, so use it. So then, after that, so why do you need to center it? Because without centering, when you reconstruct it, your Gaussian will not appear on the axis. Because here you have this, kind of shift. In fact, that's a good thing to try. Don't center it. You'll see your reconstruction will be off axis. Right? So if you center it, but then again, now when you center it, what happens to the other? Your other values of kx, you have to, set all of them to 0. So you have to, what's called zero pad. Right? Don't leave them free. They're zero pad. So then you only have non-zero values of the spectrum. And then after that, once you have that, then you do the forward or backward propagation, whichever one you want to do. And propagation is done exactly this way. And then you'll recover the original Gaussian. Are you okay with this? So that's the part that you need to do. So there are some things to do, as you can see, right? But night is finite. So start with it little bit today. Talk to yourselves, amongst yourselves, and tomorrow, you can sit in a group and work on it. You okay with this? All right, so I think that may be good enough, right?
Enough for today.
Yeah, it's enough for tonight, enough for today. Thank you. So does everyone understand every step over here? It's very pictorial. You can draw it, see it. Thank you. Yeah, actually that might stay because, well, if it stays too long, it'll, oh. All right, online guys, well, you didn't have a chance to see what was on the board.
Yes, it was correct.
It was connected.
I can see on the screen.
All right, okay, good, good, thank you.
So we are coming to an end for today's session. So I thank Professor Banerjee and also Dr. Abhishek. The morning, we have tomorrow morning lecture by Stanford postdoc fellow. Again in the evening, one special lecture in mechanical.
So that will be online or
One will be online, one will be offline.
morning online?
Morning online, evening off.
What is the sir?
Professor Akhilan talk on that because I was in the DC office, PhD student. He was working on something 3D, so he asked me to be on. That's how I know. So they called him and asked him that. So you should share some of those things. Sure. That will be out of this context, but at least some refreshing for them. And we have one participants from the mechanical background, so that will be more helpful for him also.
So there's some examples, and I will
Yes.
also have some, when two something happens, I'll have some results to show for measurement of cracks. Yeah. So that will be good.
Oh, no, strain on stress. Strain on stress.
Yes. So I showed you some examples.
Right,
of the
right, yeah.
strain and
Strain and stress.
element of. Okay, enough for today. Now we can break and meet tomorrow morning. So tomorrow morning, the online lecture time they have given